Hi folks, we're going to review the idea of extraneous roots or solutions to an equation. All right, so we're going to look at three examples to review this. So first of all, we'll take a look at an exponential equation, and let's see how we can solve this. So here I've got 2 to the 2x minus 2 to the x equals 0, and we saw that a good trick for solving these equations is to work with the same exponential expression throughout. So here I've got a 2 to the x, so I'm just going to rewrite this expression so it also has a 2 to the x. So I'm going to rewrite this as 2 to the x squared minus 2 to the x equals 0. And now I can solve this. I can essentially solve it as a quadratic equation. Okay, so I'll start by just doing a little change of variables. So let z equal 2 to the x. Okay, so I'm going to write this now as z squared minus z equals 0. And now I just have a quadratic equation to solve. So factor out the z times z minus 1 equals 0. And so the solutions to the quadratic are z equals 0 or z equals 1. But of course, it's not this quadratic that I'm trying to solve. It's the original equation with the exponential expressions. So I'm going to put back for z 2 to the x. Okay. Sorry, this is equal to 1. Okay, and in order to solve these, well, I can probably just figure it out on my own, but let's say I use logarithms to solve these. So on this one here, x is going to be equal to log base 2 of 1, and of course log base anything of 1 is always going to be 0. So there's one answer, and if I put that back into my original equation, what do I get? 2 to the 2 times 0, so 2 to the 0 is 1, minus 2 to the 0 is 1, 1 minus 1 is 0, so that works out. But when I try to solve this one here, x is equal to log base 2 of 0, well, of course, we can't take the logarithm, regardless of the base, of 0, because it's not part of the domain of any logarithmic function. So this one here becomes our extraneous solution. So while z equals 0 was a solution to this quadratic, it did not produce a solution to the original equation. And this is what this is all about. Does it produce solutions to the original equation? All right. So what's different about this first example, and the reason why I put it first, is that it's sort of very clear that you're going to end up with an extraneous solution because it comes out as part of your solving process. What we're going to see in examples 2 and 3 is that you're going to get answers and it might not be clear without testing them whether they are indeed solutions to the original equation. Okay, so let's take a look at something that's, you might have solved in earlier courses. Okay, so you've got this square root here. No way of solving it with this square root still around, so the easiest thing to do is to just square both sides of this equation. Okay, so square both sides. I square the square root of 3x plus 4. I just end up with 3x plus 4. And then on the other side, I'm going to end up with x squared. And again, I've managed to turn this equation with a radical in it into an equation that's just quadratic. So let's solve this. So I'll bring everything to the other side. So I have x squared minus 3x minus 4. So we can factor this, x minus 4x plus 1. And so here we end up with x equals 4 or x equals negative 1. And everything looks perfectly fine. There's no obvious reason to believe that one of these values will not solve the original equation. But let's see what happens when we do plug it in. So let's start with x equals 4. So if I have on the left-hand side 3 times 4 plus 4, okay, that's just 12 plus 4 is 16, so square root of 16 is equal to 4. And on the right-hand side, I just have x, which is 4. So that works out. All right, and let's see what happens now when I put in x equals negative 1. So on the left-hand side, I have 3 times negative 1 plus 4. Okay, and this is, well, negative 3 plus 4 is 1, so I just have the square root of 1 equal to 1. But wait a minute, what should I have on the right-hand side of the equation? I should have whatever the value of x is, negative 1. Well, negative 1 and 1 are clearly not equal. So that means this is, again, an extraneous solution. Okay, so while it does solve this quadratic equation, it does not solve the original equation that we're trying to solve. Okay, So here we see that sometimes you do actually have to go and check to see that your answers are indeed valid. And here we see that a similar sort of thing can happen with logarithmic functions, logarithmic equations, sorry. Now, the main thing that happens with logarithmic equations is that you might end up with an answer that produces an input that's negative into one of these logarithms, or zero, of course. Because remember, logarithms are only defined for numbers greater than zero. Okay, so let's see what happens here. So my goal is to get to a single logarithmic expression. So here I can use my first law of logarithms to bring these together as log base 6 of the product of x times x minus 5 equal to 1. Once I have this single logarithmic expression equal to a number, I can convert it into exponential form. So this is 6 exponent 1 equals x squared minus 5x. Okay, might as well multiply it out. And so now again, I've got a quadratic equation. So bring the 6 to the other side, x squared minus 5x minus 6. So here we have x minus 6, x plus 1. And so x is equal to 6, or x is equal to negative 1. Okay, and yet again, you know, these look like perfectly reasonable answers. They solve this quadratic, but let's see what happens when we input them back into the original equation. When I input 6, log of base 6 of 6, that's perfectly good. Log base 6 of 6 minus 5, well, 6 minus 5 is still positive, so that's perfectly fine. So that means x equals 6 is indeed a solution to this equation. Okay, but when I try to input x equals negative 1, right off the bat, I see that, well, log base 6 of negative 1 doesn't even exist. Okay, so how can a number solve an equation if it produces non-existent terms? In fact, even this here, if I try to input into the second expression, log base 6 of negative 1 minus 5 is still negative. Okay, so that means this is an extraneous solution. All right, so here are some examples under which extraneous solutions can occur. Okay, now the first and the third are the ones you should be most concerned with for this test here. So when it comes to an extraneous solution from an exponential equation, it'll be much more obvious because it'll come out in trying to solve that final portion of the equation. You'll just see that, 2 to the x can't be equal to 0. So it's very obvious. However, when you're solving a logarithmic equation, there's nothing that immediately tells you that these answers are not valid. You need to go and check that they indeed solve the equation, that they don't produce any terms that don't exist. All right, that's it for this one.